Hi, welcome to the next part of the Internal Forces course. Today's topic is rectangular frames. I planned the rectangular frame course similar to the beam course, meaning I wrote the internal force equations for the first part. And the second part is for more advanced students without writing equations, just like with rectangular frames. The first example was indeed about writing the internal force functions, and the second will simply be determining the reactions and drawing graphs based on the forces acting on the frame. We have an example. Calculate and draw the internal force graphs. The frame is a bit more complicated than in the previous example. We have a continuous load from above, a concentrated force on the right part of the frame, and a leftward moment. Dimensions are 2 by 2 and 2 by 4. The first thing we need to do is, of course, calculate the support reactions. In the fixed hinge support, we have two reactions, a horizontal and a vertical component. In the sliding hinge support, there is only a vertical component. So, from the sum of moments about point A, we calculate the reaction VB. Of course, we take the resultant from the continuous load, which is at the center of gravity. The center of gravity falls in this case on this side, on the right side of this vertical rod. Because at the third meter, we have the resultant, and its value is 6 times 6, which is 36. So this resultant 6 times 6 rotates at an arm of 3 meters clockwise, which is positive. The 15 rotates counterclockwise at an arm of 6 meters, negatively counterclockwise, that is negatively. For the moment 5, we take just the value, wherever it is. Its value simply, it is counterclockwise, which means negative. For me, when calculating reactions, I assume clockwise moments to be positive. It's a matter of assumption. And the reaction VB, it rotates counterclockwise at an arm of 2 meters. From this I calculate reaction VB, which is 6.5 kN. From the sum of projections on the y-axis, we calculate VA upwards, which is positive plus 6.5, so plus reaction VB, minus 6 times 6, which is the resultant from the continuous load, and plus 15 for the concentrated force. From this, reaction VA is 14.5 kN, and from the sum of projections on the x-axis, reaction HA is equal to 0, because there is no other horizontal force that this reaction could compensate for. And listen, we can verify this as well. Checking is good to do at a point. It's best to do at a point where no reaction passes through, unless a zero reaction passes through, as if it were not there. So we can, for example, do this at this point. I named it point D. So the sum of moments at this point should equal 0. And we have reaction VA, which is 14.5 at an arm of 6 meters, clockwise, which is positive, minus load continuous 6 times 6 resultant times 3 arm acting left-handed, that is negative, minus moment 5 and plus reaction VB, that is 6.5 right-handed on an arm of 4 meters. And indeed, after calculating, the left equals the right, meaning it results in 0 equals sine 0. Now we can start drawing the diagrams. We just need to remember what was in the first part of this course, which is about what signs we have depending on which section we are making, from which side we are looking, and where the bottoms are. So generally, if we make a section such that the bottoms are at the bottom and we are looking from the left side here, then the positive cutting forces are upwards, normals to the left, and moment right-handed. This is the most common section on beams that we worked with. This is a rarer section, but I also always tried to use it. In that case, the signs are exactly reversed. The cutting force is positive if it is directed downwards, and the other internal force is also in the opposite direction. The normal force from the section to the right and the left-handed moment is a positive moment looking from the right side. I indicated the bottoms here. Now to adjust this situation to a vertical rod, I would have to rotate what I have drawn here, this sign convention, counterclockwise by 90 degrees. Then, if I applied this convention, I would have the bottoms on the same side as they are here. Because I could also mark the bottoms on the other side of the vertical rod. So here I have to rotate counterclockwise by 90 degrees, and this section that I would cut this way, because I will be looking at this beam cutting it exactly this way, looking from below. Well, that would be this section. So I would rotate it to the left by 90 degrees, and that would be it, because I am cutting in that direction. Well, good. Knowing all of this, let's get started on drawing the diagrams. And I will tell you what sections I will be doing. We can, of course, do it freely here, but it's usually easiest to do it this way. One section looking from the left side, meaning we cover everything that is on that side, including that vertical rod, and the interval is from 0 to 2 meters. The second section looking from the right side, meaning this time we cover everything that is on this side, the interval is from 0 to 4 meters. And the third section I will do from below, meaning we cover everything that is from above, that vertical rod, the interval from 0 to 4 meters. Here I would potentially have two intervals, from 0 to 2, and from 2 to 4, because a moment appears in the middle of the rod. Of course, I could, for instance, make one section like this, and to include that vertical rod in the second section, I could make the section maybe in another color. Yes, but then for the section marked in red, that vertical rod also counts. And we must take these forces that are on this bar, which means that the shearing force diagram includes this force of 6.5 comma. It also shears this bar. And for the moments, we include this 5, of course, and this 6.5 also creates a moment in this red cross-section, so from this side here. And when I look from the right side, I do not see this vertical bar, that's why it's easier this way. And similarly, I could also look at the vertical bar from the top, but then one has to consider all these forces from the horizontal bars. But it is simpler as I showed you, as I marked it in green. That is the easiest way here. Well then, okay, I erase this. Now we need to do one more thing, because we are making a cross-section once from the left here, once from the right side, so we also need to divide this continuous load here at this point into the load on the left side and the load on the right side, and create a resultant from these two kinds of loads. So here we will have 6 on the left side over 2 meters gives 12, and over 4 on the right side gives 24. And it is in the middle, and here also in the middle. Now, I remind you again about the marking. So if we look at this first bar, it's like we are doing a regular beam, so on the left side we know which cross-section we have. Marking convention: positive shearing upwards, right-handed moments, normal forces from the cross-section to the left. When we look at the beam from the right side, we also know which cross-section we have. The less convenient one, more inconvenient, where it is easy to make a mistake because it is less frequently used, and the marking is exactly the opposite. Therefore, downward shearing forces are positive, normal forces from the cross-section to the right, and left-handed moments. And now it's time to think about what is happening on this column. When we make this cross-section, the question is on which side we have the bottoms, the ones I marked. So we need to rotate this marking convention by 90 degrees counterclockwise. Then the bottoms will be on the same side as we have drawn them. And cut it this way. And you see it matches. The bottoms are on the same side, meaning we need to rotate it. And now that we know all this, we can start drawing the diagrams. So the first we will draw is the normal force diagram. So we look at this cut, at this bar on the left side. And the question is whether some force compresses or stretches it. Here it could potentially be compressed or stretched by this support reaction. But since it is 0, there are no other horizontal forces. that is normal forces acting on this bar, so we have a normal force of 0. If there was any force directed in the way shown here, it would compress this rod, meaning it would act oppositely to the positive direction. Thus, it would be negative. Let's look at the upper rod on the right side. Is there any compressive or tensile force acting on it, meaning a normal force? No, there is no horizontal force. So that's also 0. Now, we move on to the vertical rod, the vertical column, so we make a cross-section here. We see that there is 6.5 compressing this vertical rod, meaning it is a normal force directed oppositely, so it compresses it. Thus, it is negative. We draw negative signs for normal forces and shear forces on the bottom side. And throughout this column, this value does not change. There is no additional force that would change anything, so it remains a constant value of minus 6.5. Well, it's a constant value. Now we will move on to the shear force diagram. We can also start from the part where we left off, which is from the column, so we are at this intersection. The question is, looking at this column from below, is there any transverse force, meaning a shear force acting on this column? Well, there is no such force. A moment appears here, but that is also not a transverse force, so along the entire length of this column, the shear force is 0. Now, let's take a look at the upper rod from the left side. Here, we have a concentrated force and a continuous load that will change this shear force value, maybe here with a different color. So first we have a jump of the shear force value of 14.5 in the positive direction, because it's in accordance with the positive direction in this cross-section. Then, since there is a continuous load, we will slide down on this diagram linearly by the resultant value from the continuous load, which is 12. So from 14.5 linearly in the direction indicated by this resultant, meaning downwards, opposite to the positive direction. Oh, that was supposed to be linear, wait. If you're having trouble quickly sketching the shear force diagram, and soon the moment diagram, I encourage you to watch the second part on beams, where I discuss this a bit slower and more thoroughly with several examples, while here I wanted to focus on something else. So the diagram looks like this. At the end, it is 2.5. Now we need to look at the beam from the right side. Here, we know that the directions are opposite, meaning the positive direction of the shear force is downwards, while this 15 is upwards, making it negative. And we have the negatives at the bottom, which means on the bottom side. So first, we have a jump of the value of this shear force of 15, and then linearly by the resultant value of 24, which is positive when looking from the right side, meaning in the positive direction, but we have pluses at the top, so this is a bit misleading. Up by 24, so minus 15 plus 24, which makes it 9 on the other side. And here it is also linear. So what can we read from this shear force diagram? We can read that here the sign changes from positive to negative. So at this point, there will be an extremum on the moment diagram. Now let's check what the value of this extreme point will be. And first, let's check at what length, looking from the left side, this sign changes, so what x will be here. If I mark x here, and the entire length of this upper rod on the right side is 4, here the entire length is 4, so if here is x, then here must be 4 minus x. Now, from the similarity of the triangles that have formed on this graph, we write that 9 to x, and I haven't marked that 9 yet. Here on the other side, we have 9. Oh, 9 is this value, and 2.5 is this one. So 9 to x, which means 9 to, this is like 15 to 4 minus x. Now from this we calculate x by cross-multiplying, and we get x equals sine 1, 5 meters. So now we compute the areas of the shapes that have formed here. If this method is unfamiliar to you, I refer you back to part 2 of the beams course. We have 4 examples. There I do it a bit slower than I will do it now. So we calculate the areas of these figures, and then based on these areas we will be drawing the moment diagram. The area of this trapezoid here is a plus b times h divided by 2, which is 17. The area of this triangle is 9 times 1/2 times 1.5 comma, which is 6.75. And the area of this triangle is 1/2 times 15 times 2.5 comma, which is 18.75. Okay, so now I think we have everything we need to draw the moment diagram. So let's start with this vertical rod. We do not have a shear force diagram here, so there is no area. But you have to remember this principle. If there is an applied shear force on the beam, then on the shear force diagram there is a jump of that value. And similarly, if there is a moment applied on the beam or frame, then on the moment diagram at that point there is a jump equal to the value of that moment. So it doesn't matter that here the area is 0 on the shear force diagram, but we will have a jump at the beginning of the rod. And afterwards, indeed, the area is 0, meaning there will be no change. It will be a constant value. The question is whether this moment 5, is it positive or negative given the bases accepted? Well, we have here a right-handed positive moment, meaning this 5 is left-handed, hence negative. And the minus is on the side opposite to the bases. So we have a constant value, and it is -5. Now let's take care of the top of this frame. So what do we have to remember? That at the ends of the beam, or frame, if there is no external moment applied, then at the ends it is 0. So both from this side as we go, we start from 0, and from this side as we go, we start from 0. And we move by the value of this field that we calculated. And now, as we move from the left side, I was doing it this way on the beams. When I used this method, I only moved from the left side, and then there was always a shift of the graph in that direction according to the sign of the shear force field, which is positive here. So towards the positive moments. I didn't do that from the right side, but now I will tell you that when we do this method of fields, if we move as if from the right side, we move in the direction of the opposite sign. Then the field shows us. Okay, so we know that we move by 17 towards positive values. We have positive moment values on the bottom side. And the moment graph is a polynomial of a degree higher than that of the shear force graph. So if it is linear here, on the moment graph we have parabolas. Well, and that is a positive value, and we finish at 17. Now let's do it from the other side. We start at 0 and move in the opposite direction from what this sign on the graph shows us. That is, we are moving towards the positive, the same direction as from the left. Now I will mark approximately where this extremum should turn out. Of course, if you decide on paper, you can do it somehow to scale. I'm not really able to do that here. So the graph ends at 18.75 for me. It starts on the right side at 0 and it should be a parabola. Well, a little ugly one. 18.75 is the extreme value. And now from this extreme value I was moving towards the positive, which is in the opposite direction from what this sign shows me, and now in the direction of the negative by the value of the field 6.75, meaning from the positive 18.75 down by 6.75, resulting in a value of 12. And I mark this skewed parabola with a plus. I finished at the value of 12. And now we have the moment graph ready. I wanted to tell you about one more thing today, the equilibrium of the node. we can establish the equilibrium of a node regarding the moment graph. When it comes to moments, well, regarding the other forces as well. But today I wanted to discuss the equilibrium of moments, the equilibrium of the node regarding moments, that is, where two or more loops converge, or some parts of the beam. We have some node. So here at this exact point. And the rule is that the equilibrium of this node in terms of moments should equal 0. The sum of moments at this node must equal 0. So we need to mentally cut out this node like this. Of course, these sections are infinitely close to this node, and we need to label the moments we have here. Right turning or left turning. Because now, so we don't mistakenly think this way, well, I know here it's plus 17, here it's plus 12, and here it's minus 5. So what would happen? 17 plus 12 is 29 and then minus 5. Well, that's definitely not 0, and that's why we do it differently. So yes, the graph here on this rod ends positively at 17, okay? So let's say this. Now the question is, in which direction does the moment turn to make it positive at this section? So this is that section. Well, it is right turning, so I will mark it. And its value is here, where the graph would end at 17. 17, now here, the graph also ends at the bottom. And the question is, in which direction must the moment turn from this side to be positive? Well, here it's the opposite of that section, meaning left turning. And that is 12. And the last rod, I will also mark it in green, just like in the graph. We have negative, and that is 5. And that is 5. So now which moment is negative? Since right turning is positive, left turning is negative. This moment creates a graph like the one we have. All right. Now we can indeed make the equilibrium of the node. So the sum of moments at this node has to equal 0. So 17 positive minus 5 and minus 12 equals 0. One more sentence about node equilibrium. You can also do it like this. I don't know if I should call it a trick. Look, if I look at that upper left rod, if I cut out the node and the graph ends here at the bottom, then the moment, which would push this graph down, is exactly this moment. Because then she pushes this chart down here. When it's curved like that, it pushes it here. If it were pointed the other way, well then no, it would want to push it up. Then take a look at this rod on the right side. Well, again, the chart ends like this. So it's such a moment. It actually wants to push this chart down here. And if it were pointed the other way, well then it would want to push it up. And here too, 5 is the same. The chart ends as I marked. So this moment wants to push it here. This is a bit of an oversimplification. Okay, that's all for today. If anything was unclear in this video, as I said, first of all, I refer you to the course on beams, Part 2, 4 examples. There I explain this method in a bit more detail. And secondly, if that doesn't help, I encourage you to ask questions under the video. I also recommend subscribing to our channel so that you stay updated with all the videos from EduPanda. In the meantime, take care. Thanks for watching. Bye.